Good afternoon. I'm Darryl Holm. I'm going to give you a lecture today, Wednesday, 17th of February. I'll begin by sharing my screen. And I will tell you some trade secrets of a mathematician, me. The trade secrets provide economic or competitive advantages to its owner, which will be you, because the information is not generally known or available through normal channels. And trade secret number one is that we live in interesting times. For example, when I was a kid, Sputnik 1 went up into elliptical low Earth orbit, October 4th, 1957. The Sputnik went around the Earth, it made this beeping sound, which seemed to worry all the adults. This became clear that they would be worried because this meant that things would change. These were interesting times indeed. It would lead to the space race, the Cold War, Cuban Missile Crisis, and more. So these rockets interested me. And I began thinking about this. But in terms of interesting times, are there any other kind of interesting times? There's the best of times, the worst of times, and it's the only time we've got. So I had an idea while I was walking home from school on that day. I looked up and I saw the moon, and I thought about these rockets, and I thought about this little satellite beeping. I thought this would be a much better target. I actually went home and I told my mother about this as a possibility. And she said, "Oh, that's wonderful. So you'll be a scientist." And I said, "Yep." And when my father came home, my mother said, "Oh, tell your father." And I said, "I'm going to be a scientist and help the Americans go to the moon." And he said, "That's the stupidest thing I ever heard of." So trade secret number two is get involved. Find someone who can help you. So after Sputnik 1, the American federal government began investing in science and engineering and mathematics at all levels of education. And less than a year after the Sputnik launch, there was a 4-year program that poured billions of dollars into the US education system. And I was there at that time for those 4 years. So that was how I got help, I got involved. So, and in the school, in my high school, when we were going through this accelerated education, after algebra came higher algebra, the year before I graduated, 11th grade. My higher algebra teacher, Dr. Thompson, taught me. He said, "You guys know how to find x with algebra, but do you know what an algebra actually is?" And he told us an algebra is the vector space equipped with a binary product. At that point, I asked a crazy question. And he said, and I said to him, "How do vector spaces get binary products?" And he said, "You see me after class. That's always the way it's been." After class, I'll tell you what he said later. Okay, see, these were very interesting times. Apollo 11 was up. Buzz Aldrin was on the moon. He landed safely. He was able to walk on the moon. These interesting times changed our view of Earth, because what Buzz Aldrin saw changed the way we think of ourselves. This is the blue marble. It's not the Earth, the place, the special place. It's just a blue marble in space. Trade secret number 3 is listen carefully. Notice things about stuff. Keep asking questions, especially crazy questions. So Dr. Thompson showed me that this quantity A with B in the brackets, which is the multiplication of AB minus BA, is not always 0. Okay, it's not just AB is equal to BA. Actually, when he said AB equals BA for the binary product, I said, like that. And he said, see me after class. Because he showed me 2 by 2 matrices. So he said to me, so you think AB is equal to BA? And I said, yeah. And he said, what do you mean by multiply? And he showed me what you know, matrix multiplication. Okay, and he showed me that this was some vector space that you could add. It had a field, it could multiply by a scalar, and that it was equipped with a binary product, and AB not equal to BA. So here's a theorem that I eventually learned. And I wish I learned it that night. I went home after class and I worked on 2 by 2 matrices, on and on and on, putting non-zero things in various spots. And sometime around midnight, I broke into 3 by 3 matrices and started multiplying 3 by 3 matrices by this rule, and realized that mathematics is power, because you can make your own rules. So in particular, you can make a rule, which is that you can have a multiplication law like this one here, okay, where for quantities called quaternions, the multiplication law is that sigma A times sigma B is some combination of sigma 0 and sigma A, B, and C, where A, B, and C is 1, 2, and 3. And the commutator of them is not 0. Of course, I never would have found that night when I first started working with matrices. But this is an entire new ring with an inverse, it's a division ring called the quaternions. And it can be represented by these 2 by 2 matrices. Hamilton found this in 1835. No, he found it in 1843. Of course, he found it in 1843. And he worked on it for the next 20 years. Okay, so asking crazy enough questions like, where does the vector space get a binary product? It can lead from matrices to quaternions that we just seen, and this can lead to Lie groups. Okay, and then that's a set of transformations of vector spaces, which don't actually have to be linear. That can lead to variational problems, variational formulations of problems. These can have symmetry, which will imply conservation laws, or the symmetry can be broken, and it will imply new laws of physics. And all this started a long, long time ago. Back when people were dealing with calculus for particle motion, and Fermat, in the 1650s was dealing with variational principles for wave motion. There was Euler and Legendre doing variational principles. Legendre solved the problem. He was 19 years old and he wrote to Euler about it. This is the problem of what is the figure in the plane who's for a certain area has the maximum perimeter. He solved this problem. It's a circle. And he wrote to Euler when he was 19 years old and said, I solved this problem. And said, Euler said, I have worked on similar problems. Congratulations. This is a great idea. Just imagine. And he didn't say, it's in my notes. Poisson was Lagrange's student. And Poisson invented an operation which was important to Hamilton. Hamilton was studying optics. It was important to Hamilton because Hamilton realized that the study of optics could be converted to the study of motion. The study of waves could be converted to the study of particles by using this variational principle here. Okay, and the particles, were moving by a flow. A flow is a map on a smooth manifold. A manifold is a space where the rules of calculus apply. And this flow could leave the variational principle invariant, which Noether saw was a way to get the conservation laws, and Hamilton needed these conservation laws to understand the solutions to his equations for motion. The symmetry was characterized by Lie, who asked what are the symmetries not of variational principles, but of differential equations and partial differential equations. Poincaré used Lie's ideas and variational principles to first of all find out the symmetry of Maxwell's equations, which is called the Poincaré-Lie group. But he also looked at what happens when you do these Lie transformations of variational principles. This started a whole category of research in mechanics and motion, and we'll be talking more about it in field theory. Hamilton's with the Poisson bracket. Eventually, this was discovered by Heisenberg that this was in fact what we needed for talking about quantum physics, where the quantities involved have both wave and particle behavior. Poincaré and Riemann set up the situation for Einstein. Poincaré saw the transformations for special relativity, and Riemann gave Einstein the mathematical basis. He also didn't have that trade secret, but he figured it out using another trade secret called tensors for general relativity. All this balancing variational principles, symmetries, and flows, and geometry all landed in Cartan's hands in the abstract form, which was completely independent of whatever coordinates you were using. I mentioned earlier, when you have the symmetry, that broken symmetry does something. Broken symmetry in physics in the last half of the 20th century was the basis for interaction of field theories, including quantum field theories. Well, maybe we'll say more about that too. Okay, here's another crazy question. What is the shape of water? This is sort of a famous poem about the shape of water, but here's the shape. Here's water in a shape. The shape looks like a brain. And if we're made of water, it would be dripping and it would sort of melt away, right? It would splash too. It would fall and splash. But suppose we think about this more seriously. In the shape of a brain, right? So shapes could change, like the way water flows. It flows by smooth and invertible maps. It has a geometry. Water flowing has a geometry, and as the flow of the water occurs, it changes the shape of the boundary of the water. And so actually, it turns out that this idea applies to anatomy and computations of how the brain might change with, some sort of growth, for example. And it turns out this is a picture of the brain, which has on it values, scalar values on the surface of the brain of something called a momentum map. This is a momentum map at the initial time. We'll come back to this idea of a momentum map. The scalar value function on the surface, which is associated with the registration problem between a source image and a target image. So is how you compare images. Yeah, we mentioned Riemann and comparing images. Remember, we mentioned Newton also. Newton said, consider a point fixed in space. Well, you could consider that for the rest of your life and nothing would happen. However, if you consider 2 points fixed in space, you can ask how far away those 2 points are from each other, and you begin to measure distances. So you could consider a shape fixed in space, or you consider 2 shapes that are different from each other, and how do you get from one to the other? How do you get from one to the other if it really is flow of water, changes of shape like flow of water? So there is an answer to this. In fact, it was already known long ago, the beginning of the 20th century, in the comparison of biological shapes. This is a picture of a drawing by Darcy Thompson of the transformation of comparing one kind of sunfish to another by putting the fish down on the table and on a grid, and then deforming the grid and deforming the drawing or the shape of the fish. So this is how the shape can change when you do this deformation of the coordinates on which you drew the initial image. Okay. So shape analysis or computational anatomy actually arose from morphology. And it's being used all the time now. I'll show you in a minute. But the problem statement for morphology was formulated by Darcy Thompson in 1917. And he said, the very large part of morphology, our essential task lies in the comparison of related forms. The flow between 2 related forms, rather than the precise definition of each form. This process of comparison or recognizing in one form a definite permutation or deformation of another lies within the immediate province of mathematics and find its solution in the theory of transformation. He learned about this theory from Henri Poincaré. What a good place to learn about transformation. You might look at his book, Growth and Form, Darcy Thompson. It's written beautifully. This paragraph is just one beautiful paragraph. They come one after another in this book. So here's Darcy Thompson's transformative approach of classifying members of species of fishes. Nice. He took it serious and look how much things changed. So modern shape studies involve a sequence of images. Okay, here we have images of a vertical slice through the brain. And actually, it's a horizontal slice, sorry. And this is an infant at birth. This is a 1-year-old child. This is a 2-year-old child. This is an adult. Okay, you see the brain develops lots in different shapes and ridges and folds. And it has left-right symmetry pretty much. And you could think of these different magnetic resonance images as a snapshots of a smooth flow. Okay. So what would be the equations of this flow? it's going to be like water, right? So it's actually going to be equations like water. And what is the flow of water? In 1966, 3 years of great work by Vladimir Arnold, between 66 and 69. Arnold changed the way that we look at flows and we look at fluid dynamics forever, because he noticed the same thing as what we're talking about is the shapes. Is the shapes of water. A blob of water changes its shape as it moves. And with this image in mind, and the idea of variational principles, and the idea of paths between shapes, the shortest path is called a geodesic. And Fermat was already talking about geodesics as the shortest path and the least time between a target and an object and a target image. And this is the same idea. And Arnold came up with the idea that the fluid flows along the geodesic flow on the manifold of smooth invertible maps with smooth inverses, diffeomorphisms, along a curve, depending on time, which is a geodesic, which measures the shortest distance between these two shapes using a metric, which is the metric of the kinetic energy of the shape, okay, of the blob of fluid, or of the flow of the fluid in the container. And he proved it by using this idea to write down the equations. Okay, so this is trade secret number 3. Ask crazy enough equations and then answer them like Arnold did. Crazy enough question is, how is shape change like the flow of water? And now the answer, or to know whether a question is a scientific question, you simply ask, does this question lead to another question and another question and another question? And that's the nature of scientific questions. So the next question is, could the ideas from geometric mechanics, the way Poincaré arranged it, or fluids, help develop shape analysis methods for magnetic resonance image registration? That's the most important thing they want to do. They want to register two images and find out the difference so they can find out how to diagnose what's changing. Is the tumor growing, for example? So Darcy Thompson's answer was transformation theory, and it was a good answer. Arnold followed this answer too. Here's a reason why it's a good answer. Lead groups of transformations of manifolds lead to momentum maps. We call it J. And these evolved by equations that Poincaré actually introduced for finite dimensions, for the heavy top, for example, called the Euler-Poincaré equations. The Euler-Poincaré equations describe fluid dynamics also, and they can be written in Hamilton's form using this thing called the Lee-Poisson bracket, so that the time rate of change of the thing, remember the momentum map in the brain, remember those colors in the brain? The time rate of change of the shape defined by the momentum map is equal to this bracket, the Lee-Poisson bracket, between the momentum map and something called the Hamiltonian, in honor of William Rowan Hamilton. And this bracket is equal to, depending on how the Lie algebra acts, the dual of the commutator AB minus BA action of the variation of the Hamiltonian with respect to the momentum map acting on the momentum map. variation of the momentum map, with the Hamiltonian with respect to the momentum map, is in the Lie algebra. It's in algebra. Okay, so a Lie group is the group of transformations that depends smoothly on a set of parameters, which so you can do smoothly, right? So you can do calculus on this Lie group, and that means the Lie group is a manifold. The manifold is the place where you can do calculus. So Lie group is a manifold, and it has a special position called identity. Okay, so here's, think of this as a Lie group. There's a special position of the identity. The rate of change of a point on the Lie group goes along one path. You may be even thinking of this path as the start and finish of an image, like the brain, or like the container, the fluid in the container at the initial time, and then later. Okay, and the velocity of the fluid as it's moving would be the tangent to the curve. And manifolds are places where you can have calculus, and calculus will give you tangents. And the tangent here can be pulled back to the initial position at the identity of the group to be a vector. And the tangent space at the identity of the group is the Lie algebra. And the Lie algebra is a vector space, right, that has a binary operation. So it is an algebra, and the binary operation is inherited. Now we know the vector space gets the binary operation from some structure to which a vector space is tangent. In this case, the structure is a group. The binary operation is the commutator on the Lie algebra, and the commutator in the Lie algebra, AB minus BA, comes from the product rule, the composition of maps. And for the composition of maps, these smooth invertible maps for transformation of shape or flow of fluid, these quantities are tangent. The velocities are called vector fields. And dual to the vector fields, in the sense of some pairing that gives you a metric, for example, is the dual to the Lie algebra. And the momentum maps live up here. The Lie algebra acts on them, and that produces this equation, which governs the evolution of the momentum map. And the evolution of the momentum map also is a way of expressing fluid dynamics. So where have we gone so far? The crazy enough equations have led to lots of mathematics. We went from matrices to quaternions to Lie groups to transformations, variational problems to symmetry, to conservation laws. From symmetries, we went to broken symmetries, and the broken symmetries, well, actually in this case, they led to old laws that applied to new physics. So if you were to say how all these maps go, you would say, for example, that a symmetry of the Lie algebra in the variational principle would reduce the tangent space of the manifold on which the problem is defined, or the configuration manifold, to the Lie algebra of the group, which is the symmetry of the Lagrangian, which goes into the variational principle and produces the equations of motion, like the Euler Lagrange equations, and comes from a variation of an interval over time, and the endpoints of the time, if it's symmetric, this quantity here is conserved. That was if it's invariant, if the Lagrangian is invariant, that quantity is conserved. This is called Noether's theorem, and this quantity here is a Noether quantity. Under the introduction of the Lie of the equivalence classes of the tangent space of the manifold to the under the action of the group, this reduces you to the Lie algebra. You go to the identity of the Lie group, and you take the variations there. You get the Euler-Poincare equations. These are in fact secretly on the Hamiltonian side of the map. By this is a map that's called the Legendre Transform. It takes you from the Lagrangian to the Hamiltonian, which is defined not over the tangent bundle, but over the cotangent bundle of the same manifold. It has elements Q and P, whereas in the tangent space, the elements are Q and velocity B. And on the cotangent bundle, the elements are the position in the manifold and the momentum sitting over in some kind of fiber sitting over the manifold. And the momentum is given by dl dq dot. So this thing is p dq, p partial q, and it's a map from the cotangent bundle to the dual of the Lie algebra. And this map, J, this is our J. P dq is J paired with something in the Lie algebra, and J is the momentum map. This is the equation for the momentum map. That's this equation here. And these are the equations on the Hamiltonian side. These are the equations on the Lagrangian side. And all these maps are equivariant. Their diagrams commute. So you can hook them all up into a cube. And Noether's theorem is on the Lagrangian side and on the Hamiltonian side. And you can go from anywhere to anywhere else on this cube by equivariant maps. So this is the structure which is underlying the question and the issue of how a vector space gets a binary operation to become an algebra. The binary operation is in the group. And there's a manifold that has a tangent space. The tangent space has the identity to the group. This is the Lie algebra. Okay. Crazy enough questions have led to lots of mathematics. This is our review of where a vector space gets a binary product. Trade secret number 4 is trust your intuition, and then check it. Now ask any athlete. The reactions to change are much better when you're already moving than when you're standing still. Me? Okay, I left. I made the decision to leave graduate school because I had a bad feeling about what would happen next with what I'd worked on so far. So my intuition made me reluctant to join academia. And instead, I went to Los Alamos National Laboratory. That has made a difference. These are the 5 mesas on which Los Alamos National Laboratory is built. This is a bridge across the Los Alamos Canyon. It's 350 feet deep. There's a little stream in the bottom. Over into the town of Los Alamos, and there's another bridge here. This is Pueblo Canyon. Out on the end of this mesa, Los Alamos Mesa, is another part of the laboratory. This is a accelerator. This is a charged particle accelerator, and a whole group of people who worked on what I was working on, particle physics. Except I worked over here in the T division building, and I'll tell you what I worked on. So this Pueblo Canyon, the bridge. This is the main mesa. This is a part of the town too. And then on the other side is another mesa. So back to trade secret number 2. So get involved and find someone who can help you. So I came to Los Alamos National Laboratory just as anti-ballistic missile devices, laser fusion, and magnetically confined fusion, big projects were just coming into the computer age. And after almost 20 years of working on plasma research, another thing came into the computer age, which was global ocean circulation. Global ocean circulation came into the computer age when parallel computers appeared, and they could now compute much faster than the vector and sequential computers that were being used earlier. And Los Alamos didn't have an ocean, but it had massive computational capabilities. So we put together a global ocean circulation group called, let's see, it's not circulation, but it's a combination of ocean and sea ice model for studying climate. You know, the climate depends on the ocean. So I started working on that. We didn't have an ocean, but we had the fastest computer in the world, and our computer would run the ocean models 50 times as fast as any place else in the world. So we could do in a week what would take a year elsewhere. So every week was fully scheduled, lots and lots of seminars, for way too many for any one person to attend them all. But one of these visitors made a big difference in my career. Okay, so now we're back to trade secret number 2. You get involved and you find someone who can help you. Roy Axford helped me. So Roy came to Los Alamos in 1974. He came to speak about Lie group symmetries of partial differential equations, like linear diffusion equation. That's what Lie did in the 1870s. But his lecture was transformative for me, because Roy told me, Darryl, read Lie. I started reading Lie, and I realized that all his work was all about vector fields, and vector fields were the language in which hydrodynamics was written, and I'm doing ocean circulation. So I have to know how momentum maps and vector fields interact, and then I started writing all the equations for ocean circulation in terms of geometry and momentum maps, and so Roy became my primary thesis advisor, you know, and I remember I had left before getting a PhD, and I went back and got a PhD in physics at the University of Michigan with Roy as my advisor, even though he was at the University of Illinois. They're both related schools in the same conference. So, and then it turned out my thesis, because I'm at Los Alamos, you can have geopolitical influence. My thesis actually affected the US-USSR threshold test ban treaty negotiations, because I found a little thing, which is part of trade secret number 3, which is to notice things and think about stuff. That's how I put this together. Okay, so trade secret number 5, take risks. Don't be afraid to fail. follow your crazy questions. Embrace failure. It's not a loss, even if it feels that way. Because with failure comes freedom, freedom to do a new thing. Why do you want to do an old thing anyway? So don't be afraid to make mistakes, so long as they're new mistakes. I'm still making new mistakes. So here's this, my task. This is that we started at Los Alamos about 30 years ago, is to learn from stochastic assimilation. This is the modern version of observed data, like tracers in the ocean, how to produce stochastic fluid motion equations, these geometric ones, whose numerics will yield the observed statistics and variability of the data. Okay, so here's what numerics looks like. This is something we calculated back at Los Alamos. It's the sea surface height and around the Antarctica. This is the Antarctic circumpolar current, the only open channel in the Earth. It runs into this Indian Ocean current and it hits it so hard that it actually knocks it back. And when it's the place where the great shear is where it spits out all these things that are called eddies, all these circulations. Now, this is the resolution of the computer. This is the resolution of the satellite. This is satellite data of observations of drifters on the surface of the ocean going back until about 1981. You can see correlations. You can see the Antarctic circumpolar current. You can see variability of the system, and you can see that it is much more refined in its resolution than the numerics is. So we need this. We need to be able to do numerics and put in data with stochasticity in the form of stochasticity to model what we don't know, because we don't know the things we're trying to compute. But data can tell us something. So this is a big data science project. We input this tracer data, we derive models for it. This is where I come in. We analyze the models, other persons in the team, simulate the models, assimilate the data, and output the model variability. We get it, we output this model variability and we check it back with the data, of course. Okay, and there's a project that we're working on this is called STUOD, for Stochastic Transport in Upper Ocean Dynamics. So here's these tracers. Here's how accurate the data is. This is an algae bloom, and that's a boat. This is a boat seen from the satellite. This is what we can do. We can improve the uncertainty until we crash down to the truth. Here's more data. This is more floats. These floats can go up and down. Okay, here's where typical simulations look like. It's very highly detailed. And here's how data looks like after it's been analyzed. I can show you a little bit more of that later. Here's how turbulence looks. You see it's close to looking like turbulence. This is 3D turbulence work done at Los Alamos. This is, someday we're going to take a cruise on this boat. Okay. This is how more data looks like. This is the Lofoten vortex off of Norway, between Norway and Iceland, just by the Faroe Islands. This is more numerics. Okay, so I thought you'd be interested to know that. Okay, so let's see if I can go back to, where am I going? Yeah, to here. Okay, so satellite data. Satellite data looks like this. Okay, so you can go to glob current. okay? And if you turn on how things move into someplace familiar, okay? So if you turn on some of the data, for example, if we look at what the satellite sees, oh yeah, looking over England and see what it sees as clouds. And we see that it has paths, right? Just paths. It also shows data of the motion of chlorophyll on the surface of the ocean. This is how we can determine how things are moving, drifting along the surface of the ocean with satellite data. If you want to know more, go to globcurrent.org. Okay, you can play with these. You can play with these issues so well. Okay, so here's temperature. Okay, this is temperature off of South Africa. This is the sea surface temperature. This is the whole story. Okay. Here's the Antarctic circumpolar current again. All right, so let me go back and finish the talk. Let me see, where was I? Okay, that was globe current. These are the models we use. All of them are wrong, but some of these models are very, very useful. These are the most detailed ones. Even though the most detailed ones, they don't have all the physics of the ocean in them. And this line here tells us how these equations change as you make approximations. And the point is, they are all these Euler-Poincare equations, again, because we know the geometry, and we know how to make the approximations in the Lagrangian, in Hamilton's principle, and then take the variations and get the Euler-Poincare equations for them. And this is the kind of stuff we're studying. And maybe I'll just briefly say a little bit about, maybe I won't. Okay, so here are the 5 trade secrets we discussed. Accept that we live in interesting times. This means things will change. Get involved and find someone who can help you. Listen carefully, notice things about stuff, keep asking questions, especially quite crazy questions. Trust your intuition, and then check it. Take risks. Use your intuition to take those risks. Don't be afraid to fail. Because failure means the freedom to make new mistakes. I wish you that freedom. Make new mistakes. Thanks for listening. Thanks very much. Thanks for the opportunity to talk to you. Bye.